All right, today we are going to talk about electrochemistry and keep going with that. We're going to talk about cell potential, work, and free energy. So first of all, says the work accomplished when electrons are transferred through a wire depends on the push behind the electrons. So in other words, how much do you have pushing behind you or behind those electrons to actually give them the push to figure out how it's going to go. Now as a reminder, 1 volt is equal to a joule over a coulomb. Where so this is an equation that we have. Q is our charge in coulombs, W is work in joules, and we need a negative sign because work needs to flow out of the system. Okay, so that's why we have that negative sign in front there. Now with work, we also have what's called a Faraday. A Faraday is a charge on 1 mole of electrons. Now this is also, I'm fairly positive, on your AP Chem sheet, where 1 Faraday is equal to 96,500 in coulombs per 1 mole of electrons. So, just as another way of saying this, where the charge is Q, mole is represented by N, which is moles of electrons, times F, in order to just kind of rearrange that equation wise. So now here comes a little bit of what's called, what I like to refer to as accepting the proof, where you see me rearrange some equations. But ultimately this last piece right here, if we rearrange work and we set work equal to delta G, or free energy, we then can incorporate a few other variables where it says this shows that the galvanic cell will always run in the direction of positive voltage and negative delta G. Okay, so two things that we stated beforehand, but here it's flipped. We've got that negative sign, so this will need to be positive and that'll need to be negative. So just kind of demonstrating why that works. Okay, so if we want to calculate delta G prime for the following reaction, we've got copper 2 is going to react with iron to produce copper solid and iron 2. All right, so we always want it to be positive. So that's why you have the little negative sign down here to reverse the iron. And so the iron is going to go from 0 to 2 plus. So here is my oxidation reaction. Here is my reduction reaction. We add that up, we get plus 0.78 voltage. So now what I can do is use the equation that we just had from the last slide. This is why I can use it, where I've got my 2 moles. Now, why is it 2 moles of electrons? Simply because there's a 2 here. All right. Okay, F is Faraday. I'm going to throw, excuse me, that in. And then there's the cell potential. So then all I do is calculate it, and I should end up with a negative 1.5 times, times 10 to the 5th, and it's going to be joules. Okay, and that's my unit because my moles, this is moles of electrons and moles of electrons. Okay, it looks like there's some extra negative signs in there, but it's just talking about the moles of electrons, so that's where we get that answer from. Okay, so that's delta G prime for that reaction. Now we want to predict whether a 1 molar nitric acid solution will actually dissolve gold metal to make 1 molar gold 3 solution. Alright, so our half reactions. First off, we would have the oxidation of gold. Then we would have a paired reduction reaction. And we are going to need to flip the gold in order to get this equal to a positive sign. So our cell potential would be negative 0.54. Okay, no, hold on, let me come back up here for a second. We flipped it because this is what we were trying to predict as to whether or not it would happen. We were trying to figure out if 1 molar nitric acid will dissolve gold to become gold 3. And clearly, it requires a lot of energy. It takes negative 1.50 volts. The paired reduction or reaction is only going to add 0.96, so this is negative, which means it is not spontaneous under standard conditions. Okay, we've talked about the fact that gold is pretty non-reactive metal, and this is just illustrating the math behind why that is the case. Alright, then we're going to talk about cell potential and concentration. Now, to this point, we've been dealing with 1 molar solutions, which have been our standard conditions. What happens if we change the concentration? Well, before we even go any further, we know if we change the concentration from a Le Chatelier's principle, that it forces it to go towards the side where there's less of something, or away from some, towards it if we decrease it, away from it if we increase it. So we got to think about that right away. So for example, if we look at the reaction between aluminum and manganese 2, we're going to predict if the actual cell that we're going to make, not at standard conditions, is greater than or less cell the cell at standard conditions. Alright, so this new cell that we're going to have is aluminum with a 2 molar concentration and manganese with a 1 molar. Excuse me. And we know it's going to shift left, so the cell will have less than the actual prime cell potential. Why do I know it's going to shift left? Again, simply from Le Chatelier's, we're adding the 2.0. This is what we're going to increase right here, so it's going to force it this way. So in other words, you're going to have less of the electron flow. Remember, we set these up so the reaction has to go this way in order to have electrons flow, and if we reverse it, it's going to have less potential and there's going to be less push on that wire. Now, if we switch the opposite direction, if this time we increase the manganese 2, well, we're going to have the opposite effect. Here we're going to increase the manganese 2 and we're going to force it forward, so we're going to have a larger actual cell potential than the regular one. So, okay. Now, the same half reactions is on each side of the same concentration. Excuse me, that cell potential is equal to 0. This is the cell where both compartments contain the same half reaction but with different concentrations. So before we've only been talking about two different reactions. Here we're going to drive it with the same reaction and just change the concentrations. Alright, so the goal is to even them out. That's what's forcing them. That's what's forcing them in order to run. And we use up the ion on the more concentrated side. Okay, lots of talking. What does that mean? All right, so we have the same reaction on both sides. We've got silver nitrate in our solution, and we have silver solid as our electrode. Now what happens, the reason, and you look at the difference here, this is 0.1 and this is 1 molar. Okay, so what happens is the silver is used up on the right, silver ion, and made on the left. And so the silver solid is then used up on the left and it's created on the right. So more importantly, the electrons will move from left to right. Okay? They will move from left to right because as that silver metal is used and it's converted to silver ion, it's trying to increase this concentration to get it equal to 1. So that's essentially where the electrons are going. Same thing if we determine the direction of flow on the cathode and the anode. Here is a much lower concentration. Here is a much higher concentration. The iron 2 plus is used up on the right and it's created on the left. So the reduction, remember, is our cathode. The iron metal, again, so the oxidation occurs at our anode, and the iron metal is used up on the left and created on the right. So the iron metal, again, we're going to try to make more iron 2. So we have iron being oxidized to go to iron 2, so we still have our same setup where this is our oxidation reaction. Over here, the iron 2 is turning into iron metal, and this is our reduction reaction. Okay, and the electrons still are transferred from left to right. So once you can figure out which way, where the oxidation reduction, which reaction is taking place, if you keep everything the same that I talked about earlier, then you can identify where the cathodes and the anodes and the oxidation, all that stuff. Okay, we got this lovely thing. Here's a whole bunch of math. Oops. To get to what's called the Nernst equation. All right, and the primary main way that we use the Nernst equation is this last one down here. Okay, here is our standard conditions delta G, our actual delta G at a new temperature with some Q value, some situation that is not at ideal conditions. So maybe the pressures are different, the concentrations are different. Then we have our equation where we had our moles and our Faraday and our voltage. So if we swap those out for delta G, we then can rearrange it in order to get to a situation where we have R times the temperature times the Faraday. And the only big difference between these two equations is that they've done this mole, because these are values, if it's always at 25 degrees Celsius, they've already done this math for you. So they've taken these three numbers, multiplied it and divided them, found 0.0591. So if it's at 25 degrees Celsius, we use this one. If it's not at 25 degrees Celsius, then we use this one. Okay? And if it's at equilibrium, as the cell discharges, concentration changes and the potential of the cell changes until equilibrium is reached. Now, if Q is equal to K and the cell potential is equal to 0, so delta G is equal to 0, at 25 degrees Celsius, the other thing that we can do is we can rearrange it to also find our log of K in order to solve those as well. So different versions depending on what they give you and what the situation dictates for you. The one on the bottom says the second one is going to have to be reversed. We know we have to reverse one of them. We want it to be positive, so we're going to reverse this bottom one down here. So we have our concentrations where we have 2.0 molar, 0.5, 0.1, and 0.1. We're going to reverse the second one, so the voltage at the primary perfect set of conditions, not perfect, but standard, is going to be 1.76 volts. And this is our balanced chemical equation. Okay, and this is making sure that everything is balanced by both mass and charge. So that's where some of the coefficients come from as well. And this is just, remember, a redox reaction most of the time takes place in either an acidified environment or a basic environment because you have excess ions floating around. Alright, so if we look at this, where do I get these from? Okay, found my 1.76, and then we're not at standard conditions, so that's where this math is going to come from. Here is my standard voltage right there, and then these are the concentrations with the exponents come from the coefficients on the balanced chemical reaction. So if we plug and chug, this is just the log of Q out here. We should end up with 1.89 volts, positive 1.89 volts for the actual voltage. All right, so actually what we did is we set these up to run it and actually have the cell potential go up. It was 1.76 at standard if everything was 1.0 molar. Now we've rearranged this to increase it to 1.89 to make it run with a little bit more strength. Alright, now for the redox reaction, here's another one. Balance the reaction, calculate the prime cell potential and the K at 25 degrees Celsius. Here are my two half reactions here. I flip-flopped the chromium-2 so that, because that's what was dictated to me up here, going from chromium-2 to chromium-3. My overall cell potential is going to be plus 0.67 volts. Excuse me, and then to find the log of K, or to find my K value, I can use this equation right here where all I need to know is the moles of electrons. I found my prime voltage, and since it's capital K, it's not going to have a unit. It's going to be 4 times 10 to the 22nd, okay? Or 4.0 for two significant figures. Really important. So again, we started adding in Q. We've kind of added in the whole moles of electrons and the cell potential, but a few other equations with which to plug and chug a little bit on this stuff. Okay, good luck. One more to go.